Balance cache affinity, friends, foes, and frenemies.
Thanks, Kirk. Thanks for the invitation. It's always great to be here in Berkeley. So just a little bit of background on me. I work at Google Research. I've been there for about 12 years, not quite 12 years. And I lead a team of about 15 people that works on optimization, mostly discrete optimization, and then we apply it all around Google, mostly to backend infrastructure systems, just trying to make things more robust, more efficient, et cetera. That's my team logo. Ask me about it later. And today I'm going to talk about a topic that just keeps coming up over and over and over and over again. And so I'm going to show you some of the times it's come up and what we've done about it. So as many of you know, cache affinity is really important for good performance of distributed systems. And the most obvious place to implement cache affinity is in the load balancer. So that's great. But it also causes really bad problems for load balancing, and hence the title. OK, so what to expect in this talk? I'm not going to assume that each of you has been working at Google for 12 years. So I'm going to start by just talking about the anatomy of a large-scale web service, and maybe old hat to some of you, but I suspect it's new to some. And then we're going to talk about caching and load balancing, right? So the basic problem is caching reduces serving costs, but it's really tricky to take advantage of it without hotspotting and creating overloads on some of your servers. And here, when I say caching, I'm not talking about on chip caches. I'm talking about application-directed caches in RAM. So then the bulk of the talk is going to be a few short examples. Those are going to be superficial. And then one very long example in depth about retrieval for web search. And if you want the clickbait version of this talk, it's right there. OK, so a couple of caveats. This is not a proper survey. Like I'm going to have a survey-looking thing at the beginning. It's not a survey. This is just stuff that happened near me. And so I got to see it up close, and I thought I'd share my experiences with you. I'll cite some papers, but it's if I don't cite yours, please don't be offended. That is just the appetizer. The main course is this thing about web search retrieval. And so, it's all of a theme, but there's going to be a breaking point in the middle where, like, if you missed it, you can wake up and you'll be fine. So feel free to give me questions all throughout. But if we get too in the weeds in the first half, I might defer some questions to the end. All right. So let's jump in. What does a large-scale web service look like? Things like web search, YouTube, et cetera. All right, so here's the user sitting up here somewhere in the world. He sends his query to a nearby GFE. GFE stands for Google Frontend. And so we got many, many, many of these throughout the world. And the Google Frontend is going to figure out some Google data center to send the query to nearby. So typically on the same continent, if it can. And it might have multiple cells. So for a cell, think of a data center. It's really a service within a data center. But so the GFE can choose one of a few cells, and that's nearby. And so then what happens within the cell? OK, so now our query is landed in the cell. Our service consists of a bunch of microservices that do little pieces of the job, and they talk to each other. And there'll be some call graph here, and it's going to be ridiculously more complicated than this. Somewhere in here, maybe one of these services is overloaded. And so you try to keep all of this in the same cell if you can, because you don't want to pay the light path cost to go between cells. But if there's something that's overloaded, maybe you're better off spilling over to another nearby cell that happens to have the same microservice running. All right. So now let's dive into what's happening at the layer of one of these links, right? So a microservice. So this is from the previous slide. What does this really mean? So each one of these is a microservice that's doing something. I don't know why that happened. But this really means a distributed job that's running on many, many different tasks across many different VMs. So here a box means a microservice, and here a box means a task running on a VM. And so you've got some client job, which is this guy, and some server job, which is this guy. And up here, you need to balance your load across here. And so load is coming in independently into this layer from whatever layer came above. And then now you've got to distribute a load across here. And despite the fact, I don't know why that keeps happening. Despite the fact that I just have 3 and 4, this is really like hundreds of tasks at each layer typically. Moreover, it's a little bit, one thing to make it even more tricky is that the horizontal scaling of these tasks, like if the load goes up, we might spin up some more server jobs or some more client jobs to handle the load, and so the sizes of these things can change. So then at a higher level, if you just encapsulate this client job here, you might be doing load balancing directly from the client task to the server task, which means that each of these guys are happening independently without communicating with each other. Or the client might have an intermediate balancer job that's sitting in between the client job and the server job. So both setups can happen. But I don't want you to think that a load balancer is just like a single machine that handles all of the traffic, because it gives you a lot of power, but it also means that you're really restricted on how much traffic you can serve. So in this case, you have some naive load balancer. So like a load balancer, if it's just load balancing and doing nothing else, then the cost of handling a query is very low. And so you can just have some crummy load balancer here like round robin, but then it can implement something more sophisticated here. Yes, question?
Motivate a little bit the assumption of identical tasks.
Ease of management.
Aaron,
Yes, sorry.
Repeat the question?
Can I motivate the assumption of identical tasks? And it's all about ease of management, right? So we have system reliability engineers who are monitoring the system all the time, and they need to be able to understand in their heads what's going on. And if things go wonky, it's just one less thing for them to think about. But it also just makes a lot of aspects of the system design easier to think about too when they're all identical. Now, when I say they're identical, what I really mean is that in terms of the shape of the VM, they have the same allocation for memory, the same allocation for CPU, et cetera. In practice, they may not actually be identical because of noisy neighbors or other issues, but it's a good abstraction. All right, so now, cache affinity. Basically, 2 examples I want you to keep in mind for this talk about what types of affinity we're talking about. The first is caching to avoid I/O, and the quintessential example there is just a distributed key value store. So here you've got some backing store that has all the key value pairs. Think of this as being sitting on spinning disk or flash somewhere in your data center. And then you have a bunch of servers, each of which has a cache in RAM that's caching some of these keys and key value pairs. Right? So the client decides that it wants to send a key to one of these key value servers, and each key value server has access to this backing store. So in theory, each of these servers could serve the key. But what's going to happen is, so suppose you send the key to one of them, it checks its cache. If so, it returns it. If not, so here key K47 isn't there, so it fetches it from the backing store, puts it in here. Maybe this guy is full, so you have to evict somebody, insert the new guy, and then you're going to respawn back. Right? But then having done that, now key 47 is there, so the next time you query this guy, you can just answer directly from RAM without going to the backing store. All right, so that's example number 1.
So the queries, where they're being directed is done by the load balancer?
Yes, that's right.
So
the question was, are the queries, where the query is directed, or is it being directed by the load balancer? The answer is yes, the load balancer is making that decision.
And that's independent of the query, in the sense that you might try to route the query to a server that might have the key.
That's the topic of this talk.
Okay.
Okay. All right. So now the other example is caching as memoization. So maybe it's not about I/O. Maybe it's about computation. So maybe you just want to compute some function, some expensive function of your query, and if you've already computed that function before, you just want to look it up, right? And so here maybe just caching the results. Okay. So that's the other big example. Okay, so now I just want to motivate cache affinity. This may be obvious to some people. Hopefully it's obvious to many of you, but I just want to go through it because I think it's instructive and it'll be good to have in the back of your minds. So I'm going to look at 3 different scenarios. And I'm going to talk about how basically how cache affinity can simulate resource pooling via these 3 scenarios. Right, so in each of these 3 scenarios, I'm going to have 10 items. They're named 0 through 9. All of them have size 1. I'm going to assume uniform IID arrivals, which of course never happens in practice, but for the purpose of this example, that's what I want. There's going to be 2 servers, and each of these items will go to one of them. And I'm going to posit that the eviction policy doesn't matter because you've got uniform ID arrivals. Okay, so scenario 1 is that you've got 2 servers, each has a cache of size 4. Each one can have 4 items. And suppose that the queries pick a server via fair coin, so you're not doing any sort of affinity here at all, right? So now if your server looks like this, then if you send any of these 4 items, you get a cache hit. If you send any of the other 6, you get a cache miss. Therefore, and it's IID uniform, so therefore your cache miss probability is 60%. And because your servers are the same, because you're just flipping a coin, it's the same for the other server. All right, so 60% cache miss rate in that case. Now suppose you have a pooled cache. Instead of having 2 separate caches of size 4, you have one big cache of size 8. Well, now things are much better. Now you've got 8 things in your cache, so your cache miss probability is only 20%. That's 20% is less than 60% by a lot. So that's good, and this, this tells you what the benefits are from resource pooling. And so for the next slide, I'm going to talk about how cache affinity can sort of simulate resource pooling, right? So if you have 2 servers, this is the same as the first one, except they're going to change what the load balancer is doing. The load balancer is going to send all even-numbered queries here and all odd-numbered queries here. Okay? So now you got 4 out of the 5 even-numbered queries here. So when an even query comes in, you only have a cache miss probability of 20%, and same for the odd queries. Right? So in this super simplistic situation, we got the same cache miss rate with the distributed cache as we would have with the unified cache. Right? And so that's really the holy grail of cache affinity. And I'll mention that this sort of cache specialization or query affinitization, this is done in popular software like memcached, HAProxy, et cetera. All right. But now, where's the rub? It's here, hotspotting. So in the previous example, we're sending all the odd keys here and all the even keys here. What if all the odd keys have twice the cost? Or what if there's twice as many queries that have odd keys? Now all of a sudden your odd server is going to melt down. So the lesson there is that the wins from caching can be easily, you can easily wipe them out if you don't load balance in a smart way. And so this really captures the difficulty that we're trying to address. Everything clear so far? Okay. So I will posit to you that the goal of all load balancing is to do the following. You want to shift or bend the throughput versus latency curve, right? So every system has some response curve here where if you increase the throughput, you just drive the system harder. There's going to be resource contention. There's going to be queuing perhaps. And so therefore the latency of your queries is going to go up. And suppose, so here's one possible curve, this orange one. Maybe that corresponds to one load balancing policy. And maybe a better load balancing policy will shift this curve downward and to the right. Right? That is the goal of load balancing, is to shift the curve downward and to the right. So what does that mean? It means that if you want to achieve the same latency with this new load balancing policy, you can get higher throughput. Or if you want to keep the throughput the same, you can reduce the latency. Right? So that's just graphically what a load balancer is trying to do. But things in the presence of cache affinity, things are not quite so simple. So there's really three regimes as load increases. If load is very low, then you don't have to worry about hotspotting. And so you can preserve affinity, and so you can send things where they're affinitized, you can save cost, and it's great. But then at a higher load, maybe some things start hotspotting. You need to move load off of those guys that are hotspotting, and now you're breaking affinity, which actually increases your cost. And so now it's a throughput versus latency trade-off when you do that. But then it's not monotone, because when the load goes even higher, now you're in a real pickle, because if you're breaking affinity all the time, you've actually increased the work that your system has to do. And if you're sort of running very, very close to your capacity, you want to stop breaking affinity. You want to actually keep affinity and just deal with the extra latency. And so this non-monotonicity is a real bear to deal with. And so the themes of the talk are, so I will say right now, we have not fully solved this. I don't think anybody's fully solved this. Maybe in certain cases we've solved it. In the web search case, I think we solved it pretty well. But this is a good open problem. So I might even say $1 billion question, as you'll see in a bit. Okay, so the themes, how are we going to maximize the computational savings from caching? And then how do you realize these savings without the hotspotting? Okay, so now we go to the, so that's the background. Now we're going to go to the appetizer, right? A few short examples, yeah.
So, is the when you're up at this overloaded system, which is the bottleneck? Is it the back? Is it the all the misses, serving all the misses, or just like the front end traffic? What is the throughput bottleneck?
It depends on the system, but it can. I mean, it's right. I stated this in a very generic way,
Yeah.
so generic that I can't answer your question. Sorry, should I repeat the question? The question is, where is the bottleneck? Is it just the overwhelming amount of traffic, or is it the misses? And it's going to be a combination of the two, and which it is will depend on characteristics of your system. Is it this I/O bound thing, or is it the CPU bound thing? Is it, or TPU bound thing? What's your load balancing policy? So I can't answer your question in general. It could be either or both.
So, but that would impact what decisions you make, right?
Yes.
Okay.
Yeah. And you're going to have to sort of react dynamically to what you see on the ground. Okay, so what's kind of the classic way of, or a classic way of dealing with cache affinity? So I'm going to talk about a hash ring. Many of you have seen this. So you have the bins that you want to affinitize your items into. Your items are these balls that are going to get thrown into the bins. You just hash them all into a circle, and then each ball gets thrown into the first bin clockwise. So therefore, this is the only one that goes into A. 4, 6, and 3 all go into B, and 5 and 1 go into C. Okay, that's an interesting thing. Random things are kind of uniform, blah, blah, blah. Maybe this is what we want. But there's a big problem that, as I said before, these systems get resized all the time. Maybe you add or remove servers. And so if you remove this server, you're in really bad shape, because now all 3 of his balls are going to get dumped into this server, and now you have a 5-1 split. And obviously the 5 and 1 are partially because these are small numbers, but it's, the problem is real. So, okay, what's a partial solution? There's this virtual bins idea that goes way back to the Akamai paper in '97. You're not going to hash each bin once. You're going to hash each bin k times. So they're virtual bins. And so this A1 and so A0 and A1, whatever balls go into each of these become the balls that go to A. So now, right, so here, right, what's going into B? 6, 3, and 1, because 6 and 3 go into this version of B, and 1 goes into this version of B. And now what happens if B disappears? Well, this portion goes to C, and this portion goes to A. So you're not dumping, if one bin disappears or one set of virtual bins disappears, you don't dump everybody into the same bin. So that's a very desirable property. Still though, if you think about it a little bit, you're still going to have imbalance in the load. And the imbalance can be particularly bad because, like, if you just add up the sections of the circle that any one set of virtual bins has, they sum up to 1 over all the virtual bins, and some virtual bin is going to have at least 1 over n, or even in the equally balanced case, even if you're super lucky, all the virtual bins or all the the A, the B, and the C each have 1/3 of the circle, but you can still have a lot of imbalance just from randomness and where the balls are. So there are various variants. Yes?
We're talking about tens of thousands of balls and bins, right?
Yes.
So, I mean, these issues, these kind of spikes, 1 over n is really small in that case, so why should I care?
Yeah, because you're still going to have normal distributions, roughly, and that's still enough variance to cause trouble.
Huh.
And because here's the bigger issue. Each of these balls in a typical thing might be a connection or some sort of request. The requests themselves are very non-uniform. And so if all you're doing is balancing balls, that's not necessarily enough to actually balance load.
The more weighted balls or something?
Yeah. But then the bigger problem is you don't even know the weights usually ahead of time. So you got to do things that are more reactive. I'm not stating this as the end-all be-all solution. This is a starting point.
I'm just trying to understand. Yeah.
Yes.
Yeah, actually, on that note,
Yes.
so, if you transfer 1 over n to somebody else, that's like doubling their load. But in
Yep.
this case, you're doing 1 over n by one sort of.
And by k if you've got k, yeah.
What, I guess maybe you could, of course, increase K and try to make that as small as possible, but
Yes.
there is a cost to that.
Yeah. So there's there's a lot of work. There's a lot of work on that. That's not really the focus of the talk.
Okay.
But yes, by increasing increasing K, you can make things better. But it still doesn't fully solve the problem. You can, however, there are variants of consistent hashing with bounded loads. The basic idea there is that you give some capacity to each bin, and when you assign, I don't know why that guy keeps coming back. Okay, when you assign a ball to a bin, you just sort of keep track of how much load is in the bin when you assign the ball there, and if it has exceeded the capacity, you just forward it on to the next bin. And if your hash functions have some particular properties that they achieve in this paper, then you get lots of properties you like, which is that not too many balls move around when bins come and go, et cetera. And I'm deliberately obfuscating some of the details because of this. So this is a really, really nice application of that paper that doesn't quite use the paper as written. This application is also not from our group. It's from Vimeo, which is like 3 blocks down the street. So Mikkel, Vahab, and Morteza in my department, Mikkel was visiting at the time, they published this paper, put it on archive. It hadn't even hit SOTA yet. And somebody down the street picks it up and says, oh, this solves the problem I have. So Vimeo it's a video platform. I don't know if anybody's used it. Their shtick is that they host high quality videos. So they have this dynamic video packager called Skyfire. And so basically when you want to grab a video, they're going to grab it from you from different servers in little small chunks. And so they need to have some index that says, if I want the 2-minute time point of this video, what chunk of bytes does this actually correspond to? And instead of pre-computing these indices, they actually compute them on the fly. And so this is the memoization version of cache affinity that I was talking about before. So you send a request for a video segment to some server. It computes the index on the fly, and then hopefully other requests for that same video will go to that same server, so they don't have to recompute the index. They also have both this task level cache and also a cell-wide cache. And so it's actually both memoization and retrieval, sort of the combination of the 2 examples I said before. And until discovering our paper, they were running with, well, first they did some sort of cache affinity using virtual bins, and they couldn't deal with the hotspotting, so they turned it off. And so then they ran with least connections load balancing, so they're just trying to balance the number of balls in bins by explicitly enforcing that. And I think their system might have been small enough that they could handle that they had like a single load balancer, so they could actually keep the full state. It wasn't clear from their blog post or from talking to the guy. But anyway, they're doing least connections load balancing. And then they found this paper, and they're like, oh, this is the solution of my dreams. They implemented it, and this happened. So, okay, this happened. So what's happening here? So this is the overall cache hit rate for the cell, with that split between local is green, so green is good, and yellow is remote, which is not as good. And so now they're getting way more local cache hits, and their overall cache hit rate stayed the same because at the cell level they're doing the same thing, but most of them are local now, which is fantastic. Because they had a higher cache hit rate on the local caches, if you look at the overall bandwidth that they're sending to the cell-wide cache, it dropped precipitously, something like 8x. So we just really love this. We loved it for many reasons. One is that, that's just really satisfying to see. We also had some internal applications, but this one has nicer pictures. So I'm sending you this one, showing you this one. But it's also just cool because this is an example where publishing makes a difference, right? You get your ideas out there and then they get used. So we really like this example. I'm about to move on. Any questions about this Vimeo one? Okay, so here's a different approach to cache affinity. There's a system at Google called Slicer. It was described in a paper in 2016 by Adi et al. So this is sort of auto-sharding your key space, sort of middleware that would sit in between your application and basically between two microservices. So you kind of just plug it in and it should work. Okay, so what's the approach that Slicer takes? It takes its keys, it hashes them into a 63-bit key space. I assume they're doing something with the other bit, but I'm not sure what it is. Okay, so then they slice the key space into some smallish number of slices, and each of these slices you're going to keep track of explicitly. And then you're going to place slices on tasks, and you can have multiple slices per task, and you're going to also replicate the slices multiple times for redundancy and reliability. And then when a request comes in for a key, you see which slice it's in, you see which task has those slices, and then you load balance amongst those. And I think in their case, they're just load balancing basically evenly across those, maybe a round robin or something. And then how do they deal with hot spotting? Well, if they have a slice that's getting too much traffic, they can split it in half. Now you've got two slices. You could replicate it more times so you can split the traffic more ways. They deal with things that way. One big problem is suppose you have a single key that's really, really, really hot. One weakness of the system is they slice it in half many, many, many times until they get down to just one key, and then they end up having to replicate that key many times to deal with the hotness. So, it's not perfect, but there are a lot of systems at Google that use it to good effect. All right, this one is something that's using some technology that I actually was involved in from this paper. So one of our collaborators at YouTube used a load balancer we built for this application, right? So there's some microservice that has a very, very small number of tasks per job and an enormous reduction in cost on a cache hit. So what they do is they use our load balancer to actively probe each of those tasks and just say, do you have my data? Do you have my data? Do you have my data? And the ones that say yes get very, very strong preference in the load balancing scheme. And they don't do anything too principled. I think they just multiply the score by 10 for the ones that don't have it. And this worked really well in this case. And so this is just a little side pitch for another project I really like about this load balancer that does active probing. When you're actively probing rather than just passively listening, you can do some really interesting optimizations like this.
So could you just elaborate what actively probing versus passively listening?
Yeah. So if you go back to that slide where I was talking about the clients and the servers, the way things normally work is the client gets a query. It has some information that it's learned in the past about the servers, and it makes a decision. And this load information it got from piggybacked information on previous queries it had sent to the servers that it got back. And so that information is inherently a little bit stale. If you actively probe by just sending a very low-cost RPC that says, what's your load now? And then make decisions based on that, then you can piggyback on that and also ask, oh, not only is what's your load, also do you have this key in your cache? And then you can do some cool stuff. But even without that cache affinity piece, it's actually quite effective.
So when you say every cache, so that seems expensive.
There were a small number in this case, very small number, like 2. All right, so here's the billion-dollar question, right? LLMs, everybody is very interested in those these days. For that reason, I can't say too much about this, but there's something called the KV cache. That's just the intermediate state that a transformer uses to help it produce the next token, right? And so if you have the KV cache for the current state of your conversation, plus the model weights, that gives you the next token that it's going to output, plus the next KV cache. And so chatbots, like Gemini, will store the KV cache for prefixes of some conversation. So if you have some conversation with Gemini, then you go away for a day, and then you come back, it wants to pick up where it left off. And so if you didn't go away for too long, that data might still be in cache, and then it can save a lot of computation. So basically, it's just going to go to the last snapshot that it has, and then it'll recompute from there and then pick up your conversation. So doing this well is really important, saves a lot of money. and a lot of TPUs. But as I've said before, it's hard to get it right, and the reason it's hard to get it right is this preserve, break, preserve affinity business I was talking about before. And I'll stop talking now before I get fired. Yes?
I want to ask two sensitive question. On the order of what's the rough size of a KB cache if you have to keep it around between conversations?
Big.
Gigabytes. Okay, fine.
Very big. Okay, so that was the appetizer. Now we're on to the main course. All right, so in other words, if you haven't understood anything so far, that's okay, because we're going to kind of wipe the slate clean and you can start paying attention again. So wake up. Here we go. So we're going to talk about web search retrieval. Okay, so what's the main result? Main result is that in the web search backend at Google, we have some optimization that reduced misses in an important cache by 2x, which relieved a bottleneck. If you don't know what postings list is, that's okay. I'll tell you in a minute. What was the impact of this? Well, this was not the only bottleneck in the system. There were other ones, and so we ended up increasing the throughput by 40%. But what does that mean? That means that every data center now does the work that 1.4 data centers did before. That was a big deal. And then our technique is applicable elsewhere, so I hope you'll see. I mean, hopefully one of you will see this and say, I've got a system that could benefit from this as well. So I'm going to go through now and explain all these terms. This is the main result. Okay, and so the crux here is sort of what I said in that example before. Ideally, cache affinity allows you to get the benefits of resource pooling even though your cache is distributed. This is different though, because search queries, not many people issue one-word search queries. Actually, plenty of people do, but most interesting search queries are more than one word. I think at some points in time, the top query on Google was Facebook, because people couldn't be bothered to type facebook.com. Anyway. Anyway, so right. So most queries are multiple keys, and so now we can't just that makes things more complicated, as you'll see. All right. So you've seen this picture before, except the difference here is that now your query has multiple keys. These keys are terms in your search query. Right. So here, for various other architectural reasons, we're not going to send different keys to different places. We're going to send them all to one server, which is going to do a bunch of computation on all of those keys. And therefore, we care about whether each of these keys is in cache. And so here, you got 3 keys. This cache has 2 of those 3 keys. So that seems pretty good. Let's send the query there. We have a cache miss on key 17, so we'll have to retrieve that from the backing store. Okay, so it's very similar to the previous thing I showed you, but now we just have multi-key queries. Okay, so outline for the rest of the talk. I'm going to give you a primer on web search engines. How do they work? I'm going to tell you about this TARS voting scheme. TARS stands for Term Affinitized Replica Selection. After I named it that, I also realized it was a robot in the movie Interstellar. Should have put a picture of him here. So I'll tell you what the TARS voting scheme is. I'll tell you how to create a table, the voting table that's central to this voting scheme, using some cool discrete optimization, particularly balanced graph partitioning. And then I'll show you some experiments, and then we'll wrap up. Yeah?
In the multi-key case, isn't the case that there is some computation the server is doing on the collection of keys before sending the result? Because
Yes.
otherwise, if you're really trying to save...
Yes. Yeah. So what's happening here in the web search case is you send your query somewhere, and one of the many things that okay, so this server is going to compute the entire answer to your query. But it is one of the pieces is it has to retrieve some data for each of the terms, and that's why it all has to be on the same server. Okay. All right. How do web search engines work? Or at least ours. All right, so 2 main steps. The first is retrieval. That just means find all of the documents that contain the query terms. Second piece is scoring and ranking. So take that set of documents, rank them, and decide which ones to show to the user. What are we trying to do? We're trying to maximize the total throughput. QPS is shorthand for queries per second. We care a lot about latency, so we want to keep everything within some latency bound. And to do this, you have to have vast horizontal scaling, right? We have many data centers that are doing this. Your query goes to one of them. Within that, there's many, many, many machines that are working on it. OK, so let's look at this retrieval piece. Sorry, so I should have mentioned this talk will be about the retrieval piece. We're not talking about the scoring and ranking. OK, what is retrieval? So I had this term before, postings list. Postings list is one of the things, it's sort of like the TLB before. I wish I could rename it. I don't even know where the name comes from, but it's old. What does it mean? You just have a term, document, incidence matrix. Postings list just means a row, a row of that matrix. So here we've got some sports terms. Here we have some document IDs, right? So each document just gets an ID. And there we've got the incidence matrix. And you got a bunch of well-known sports, although you might not know this one. So that's flat ball, my favorite sport, and that's my favorite player. OK, so when you're doing retrieval, you want to do an AND of the retrieval term, the terms in the query. You also, there's more complicated things that can happen upstream of the system. So there's something called query rewrite, where your user query gets expanded into multiple different queries, like incorporating misspellings and things like that. But by the time it gets to this system that I'm talking about, we're just doing an AND of all the queries, which just means an intersection of the sets. And so if you're doing an AND of soccer and flatball, documents 9 and 1 are the only two documents that are in both postings lists. So in a nutshell, that's retrieval. OK, we need to split this work up amongst a bunch of different computers. How are we going to do that? There's two ways that have been tried in the past, doc sharding and term sharding. Term sharding is where you divide the matrix that way. And doc sharding is where you divide the matrix that way. I think early systems did term sharding, but it was a real pain. The control flow for term sharding is real pain because you end up having to bounce the query across different machines, and you don't want to do this. So I think pretty much every company has moved to doc sharding, which is where you basically split the web index into chunks. And the nice thing about doc sharding is that you can completely answer your query for shard 1 without looking at shard 0 or 2. Right? And so each of these shards is going to be searched independently, and then we can merge the results at the end. OK, all right. So here's the most complicated slide of my talk. Hopefully, it'll make sense by the time I get to the end of it. All right, so here's a schematic picture of a search cell. The terms we use internally are leaf and root. The terms we use that sometimes you see in the literature are index server and query broker. I'm just going to call it leaf and root. So here you have the roots. So basically, at the top of this system, queries are coming in. They've already been hit query rewrites, and now you're all that these guys are doing basically is they're going to farm out the queries to each of the shards. So here what we have is, in this picture, I've got 3 shards, although in practice it's many, many more. Each of these shards is replicated. So here we have 2 replicas, although in practice it's more. And so for each of these 3 shards, the root has to choose one of the 2 replicas. So in this case, the query came into root A, and it decided to choose replica 0 for each of the 3 shards. But it didn't have to. It could do replica 0 here, replica 0 here, and then it could do replica 1 here if it wanted. The point is, it makes S different decisions, 1 for each shard. And within that shard, it has to choose one of the R replicas. What are the bottlenecks in this system? OK, first of all, what do these tasks look like? So they got a bunch of CPUs running. Then within RAM, they have two categories of postings lists. They have some postings lists that are just pinned in RAM. So these are the ones that are so big. These are terms that just appear so often on the web that you don't want to pay the latency hit of ever having to retrieve them. And so you just pin them in RAM. They're just always there. Fortunately, there's a strong correlation between the length of the posting list and how often it's accessed, because the terms that are popular on web pages are also the terms that people are search for popularly. not always, but there's a very strong correlation. So that's nice. You got these big and hot PLs that are just always in RAM. You always hit cache on those. And then you have this cache where things can be evicted, right? So these are the ones that are just like been used recently. And so when a query comes in, you have to look. So suppose this query has 2 terms, and suppose T prime hits cache, T misses cache. So now you've got to go to the PLs that are stored on flash. Of course, they're stored separately for each shard. And then you have to load that into cache here. Now note, I've drawn this way. These PLs that are on flash, they could be stored locally on a local SSD, or they could be stored remotely over the network. For the purposes of this talk, it doesn't really matter which. So that's the overview. That's what happens. So they do the retrieval, they do the ranking, they send the results back to the root, and then the root just assembles everything together and decides what to return.
Do all the pin PLs contain the same data?
Within a shard, okay, so everything, yes. Within a shard, yes. So these 2 replicas are identical. They're identical in terms of the pin PLs. But this shard is different because this is a different piece of the web, and this is a different piece of the web. Right, so you divided the web into S equal pieces, roughly, your doc index.
Okay, but like, I don't know, say like Taylor Swift or something, right?
Yeah.
So all copies of all replicas would have something pinned for Taylor Swift for their
I see. Yeah,
their
so
documents.
this is a design choice, but yes, we would have Taylor Swift would be pinned everywhere. But the data for Taylor Swift would be same data here, but different data here and different data here because it's different chunks of the web. Good. Any other questions about this? Go
You'll
ahead.
need to broadcast the query to every shard. That's for
Yes,
every-
one replica of each shard.
Yeah.
Yeah.
Will that be expensive? Like given
Yes.
the number of shards?
What's that?
I mean, given the number of shards, can this be expensive to do this broadcast and scatter?
It is expensive. It's expensive, but it's not nearly as expensive as the computation that happens within each shard, right? Because basically all that's happening here is this is an RPC. You just package up the query, you serialize it, you send it out. But then this one is doing a lot of work, right? It's searching the whole web for that. Well, not the whole web, but it's 1 over S chunk of the web for that query. So yes, it's expensive, but it's a small cost in the overall system. Anything else? Right. So for the rest of this talk, we're going to be focusing on what's happening at a single root, making a choice for a single shard. And then, of course, this thing is happening in parallel for all shards, and other roots are doing their own thing. Okay? All right, if there's one thing I've learned from working in applied optimization, it's that the very first thing you should do is get to know your data. So let me tell you about the data we were using for evaluation before I even talk about the algorithms. So we collected 9 query traces. We collected them from 3 different regions. So because we're trying to send queries locally, most of the queries that land in Asia started in Asia. Not all of them, but most of them. Same for Europe, US. So for those 3 regions, we collected 3 query traces each. We used one of them for training, one of them for validation, and one of them for test, as all good ML people should do. And so here's a really interesting thing. Despite the fact that the Asian queries are mostly coming in Asian languages, and the European queries are coming in European languages, if you look at each training trace, each query trace, and represented as a vector of terms, where each term is basically the total number of pages, PL size requested. So so each of these things is going to be a vector. If you compare those vectors using Jacquard similarity, it's actually quite high. So between train and test on the same region, you expect it to be high, and it's about 96%. But even across regions, it's above 50%. Yes?
In one sentence, what Jacquard similarity is? Or
Yeah, Jacquard similarity is if you take 2 vectors and you take the min of the 2 vectors component-wise, and you take the max of the 2 vectors component-wise, then you take the L1 norm of those 2 vectors, and then divide them. That's the Descartes similarity. So basically, it's just a measure of saying, how similar are these two vectors? How much overlap is there? If it's a non-weighted version, then it's really just the intersection over the union. But I was looking at a weighted version here. Okay. And why is this? I don't know. Maybe because a lot of people search in English anyway? I'm not sure. Yes. So, no? Okay. There's a lot here, but let me just point out a few interesting things. So in the training set for North America, we had almost 8 million queries. Most of the queries appear only once, right? So there's only fewer than 9% of the queries are actually ones that have been repeated, right? So what that tells you is that if you're just trying to do something based on popular queries, it's hopeless. Most of the queries are not popular. That's a little bit of a cheat. Actually, there are popular queries, but those get filtered out by a cache that's sitting above the system. The second is that most terms appear only once. 67% of the terms appear only once. If you're trying to cache data that's based on terms, and most of your terms only appear once, it gets pulled into the cache, and then you never get to use it again. This just sounds hopeless from the get-go. But remember what I said before about how the postings lists that are big are also the ones that are popular? Most of these terms that occur only once have very, very short postings lists. And so if you just look at the weighted, if you just look at the total number of pages of memory that you would have to pull in for those things that only appear once, it's only 0.15%. And so that says, okay, great. All right, so 0.15% is going to be a lower bound on our cache miss rate. I can deal with that. If it were 67%, we'd be in bad trouble. On the other hand, it's still kind of challenging because if you look at the total accesses per query, it's still only just a little over 4. So unless you have good cache locality or locality in your stream, those ones are going to be hard to get cache hits on. And then moreover, this is just a statement about the size of our stream. The largest cache we'll use, I'll call that S5, you'll see why later. If you look at the total amount of data that needs to be brought in over the course of this stream divided by that cache, it's 1919. This is a cache that was tuned to have miss rate 5%, which means the cache will turn over 95 times over the course of one play through these logs. So basically, I just put that there to assure you that we're not playing any games. This is a big enough trace to be meaningful. Okay. All right. So now we're going to get to what do we actually do. All right. So in one slide, this is what we did. There's an offline piece and there's an online piece. So the first thing we did is we took these offline query logs, the training logs, and we did some clustering of terms, and I'll show you exactly how we did that in the coming slides. So we clustered these terms. Based on that term clustering, we created some voting weights. And those are encapsulated in some table that was computed offline and loaded into the roots when they start up. Okay, so the roots just all have this common voting table. That's the offline piece. Those are all the dotted dashed lines. Then there's the online piece. So you got some incoming query. Oh, and in the offline piece, right, I was doing this term clustering. And so suppose that you had only 2 replicas, and maybe one of them got all the sports-related terms, and the other got all the clothing-related terms, right? So now your queries come in, and so each of these terms is affinitized to one of these 2 replicas, which is color-coded here. And that's great. If you get LeBron James basketball, it goes here to the sports, no trouble. But what if you get tennis shoes? Well, tennis is a sports thing. Shoes are more of a clothing thing. Where should you send tennis shoes? And that's the difficulty we're going to try to resolve in this, what follows. Is that clear so far? Yes?
So is the clustering helps if most of the terms are distinct?
Sorry, what's the question?
You said previously that most of the terms are distinct, right? So how does clustering helps then?
It's because of this.
How
It's-
does clustering help?
Oh, yes,
Question.
sorry. The question is, if most of the terms are distinct, how does clustering help? The way it helps is because of this. Most of these terms that appear only once don't actually pull in that much data. And so you're just in bad shape for those terms. There's nothing you can do.
Okay.
But fortunately, it doesn't hurt you by much.
Okay, thank you.
Anything else I want to say? Right. So is this part clear? Because if this part is not clear, you're going to have trouble with the rest of the talk.
Can you explain again? So what it says replica 0 leaves are those and replica 1 leaves are those. I don't quite understand.
Yeah,
I thought the both
so-
replicas
so
are
re-
the same thing.
Yeah, so remember that that you've got R times S servers. There's S shards and there's R replicas. So here, I'm grouping these by replica. So these are all of the shards of this replica. Before it had it grouped by shard, but now I'm having it grouped by replica. So, and these are all of the shards of replica 2. So suppose there were just 2 replicas of each shard. These are the S different shards of replica 0, S different shards of replica 1. And at first blush, what we're going to try to do is, to a first approximation, what we're going to try to do is, for each query, we're going to choose a replica and send it to that replica in each shard. I'll modify that later, but that's what you should have in your head. David.
And presumably at some point, there's a design decision based on other metrics of how you're doing the cluster.
Yes, that is the crux. We'll get to that. So the question, yeah, presumably there's a design decision based on other metrics of how you're doing the clustering. I'll show you exactly how we do that. Ben.
So the way you've drawn the example here, the clusters are disjoint, but then the example you gave shows like maybe you don't want disjoint clusters.
Yes, that's also one of the key things I'll have to deal with. So the clustering, we will do a disjoint clustering. What ends up actually kind of being in cache on those replicas will not be disjoint. Yes. I mean, unless the clustering were perfect. Like if your language really did cluster and you never use a query with these two, yes.
It seems to me that you're now combining the horizontal partitioning and vertical partitioning of that matrix. Is that
No, we're not. And that's because what's actually happening on these, it's actually happening on each of these things. Like each of these little cards here is one vertical slice.
Yes.
Yeah.
And you have these 2 parts, which is actually a horizontal slice.
So here's the thing. Each of these things can actually handle every term you might send to it. It's just that these are the terms that are going to happen to be in cache. These are the rows that, so it has a given vertical slice. And for these rows, they're going to be more likely to be in cache. And the other rows are less likely to be in cache. And therefore, they'd have to go to Flash to grab them.
Are you allowed to, sorry, and maybe this is what the other questions you're asking, but just explicitly, are you allowed to have replication of terms? Are you allowed to put shoes in multiple shards?
So yes and no. So the postings list for shoes, sorry, in multiple shards. The shards are about sharding the document space, not the term space. The terms are really just about which terms do you want to be more likely to be cached on a particular replica. So if you look at these 4 yellow tablets here, that will allow you to search the entire web. Each tablet is a 1/4 slice of the web. Okay. Now within web slice 0, you have all the possible terms, but these are the terms that are more likely to be in cache because we've been sending more queries there that involve these terms. Does that make sense? But tennis could very well end up here. If you sent tennis shoes over here, then tennis will have to get pulled into cache here. And that will happen even though we didn't necessarily want it to happen.
So the cache content is a side effect of the documents that are there,
The cache content is a side effect of what queries you sent there.
which then is downstream of the documents that you put there?
So there's this, if we go back here, we are once and forever splitting up the documents into shards. So these documents can only ever be accessed when you query shard 0, shard 1, shard 2.
Yeah.
Now let's focus our minds on a single shard because it's just a smaller version of the web. So forget about shards from now on.
I guess it goes to, but like a query gets processed by a server because of the documents that are in it.
Right. So no, actually a query will get processed by one server that has these docs, one server that has these, and one server that has these. It's just that this server is replicated R times, this one's replicated R times, and this one's replicated R times. So you choose one of these R, one of these R, and one of these R.
I guess it gets that initial processing, but then one of them has to do the final, has to like actually finish the work, right?
Yeah, that happens at the root. So each of these shards does some work, sends its result back to the root, and the root collates things.
Okay, okay.
All right. So basic version of TARS, what are we going to do? We're going to compute this table of voting weights. What does that table look like? I'm going to set things up such that the voting weight for term T against replica R is the expected number of page misses if that term T goes to that replica. And you can rightly ask, how the heck am I going to get that number? Hold that thought. Then online, when the query Q arrives at the root, so that when the query comes here, it's going to consult this table. And it's going to say, all right, for each term in my query, I'm going to sum up these voting weights against replica R. That's going to be the total expected page misses if I send that query to replica R. So when this number is big, you're unhappy. And you want to be minimally unhappy, so you're going to choose the replica that minimizes that vote. And so in other words, you're just trying to minimize expected page misses, assuming that these numbers are accurate, which is quite an assumption. OK? Full version. All right. You also have to balance leaf CPU with these leaves. And so if you just affinitized everything to one replica and you sent all your queries there, the other two would be sitting idle, and that's no good. What is our solution to this? And this is not really the focus of the rest of the talk. This is pretty much the only place in the talk where I'm going to talk about this. But we're going to maintain a multiplier for each replica that's talking about how overloaded it is. And ones that are super overloaded are going to get a higher multiplier. And this multiplier is going to get learned over time, and it's going to be very dynamic based on the current load. So we're just using an integral controller to update these m sub r terms. And then the root is going to multiply. So before I was doing argmin based on this. Now I'm going to actually multiply by this multiplier and then take the argmin. So if the multiplier is high, you're less attractive and you get less traffic. And one interpretation of these multipliers is if you take the ratio of two multipliers, it tells you I'm willing to have, if the ratio is, this is 1.2, you're saying, well, this guy is so hot on the CPU side that I'm willing to have 1.2 times as many cache misses as I got here and still, this guy could have 1.2 times as many cache misses as that guy, and I'm still happy to send the traffic there. Right? So it gives you this smooth trade-off between your cache misses, which are hitting your flash I/O bottleneck, and then your CPU. As I said, I will not talk about this in the rest of the talk, but this is just to set your mind at ease. We do have a mechanism for getting rid of hot spotting, and this is it. The rest of the talk is going to be about how do you minimize cache misses. All right, so in other words, we just assume that all these weights are 1 now. You might ask about the cache eviction policy at the leaves. what I'm going to talk about is sort of orthogonal to that. Use whatever policy you want as long as it's a good one. The experiments we ran used LFU. We also ran it using LRU, got basically the same results. What we have in prod is a little bit different, but still similar results. So we're just going to focus on training this voting table. That's really the crux of everything. How do we maximize the benefits of caching? Now notice, so this gets at some of the questions that I think you had over here. You're asking how do things end up in the cache? Well, you have this table of voting weights. Those weights will influence where the where the queries go, right? So you got the query arrival process. They'll send things here, and then the PL eviction policy also will influence what's in the cache. So all of that will then tell you what these cache occupancy probabilities are. And then if this is the probability that you're in cache, that's the probability of a cache miss. If you multiply that by the size of the postings list in pages, then you get the expected number of cache misses. Okay? And so what we're going to do is we want, okay, and of course then that would give you a new voting table, which may or may not equal your initial voting table. If, and this is a big if you could find a voting table where this set of W's equaled that set of W's, in other words, an equilibrium voting table, then everything makes sense. Yes?
So these weights are based on terms, right? So T.
Each term and each replica has a weight, yeah.
But the queries are sets of terms.
Yep.
So and then you're adding up all of
Yeah,
them.
so that's the W became a V by adding over all the terms. So now you get the total cache misses
for a given
replica. Yeah. Good?
I think I don't know if there are correlations amongst terms.
Yes, there are correlations amongst terms. We're getting there.
Okay.
Okay. How do we train the voting table? Okay, here's what we're going to do. We're going to cluster terms by frequent co-occurrence into R clusters. Let's say that cluster R is the favored replica for a particular term. And this clustering will give us an initial voting table in a very naive way that I'll show you in a minute. Then we're going to repeat until we get to an equilibrium. We're going to take the logs in our cache simulator. We're going to run the logs through the cache to estimate these occupancy probabilities. And then we're going to use that to refine the voting weights, hopefully in such a way that this difference of the old weights and what the new weights would be goes to 0, right? That's the strategy. So get some initial good thing and then do basically gradient descent, as it were.
What is SZT? What is that?
The size of the postings list for term T. Yep. All right. I love this quote. George Box is a statistician who wrote a paper in 1976 saying all models are wrong, but some are useful. You're going to see some examples of that right now. So some notation PT, that is, so I'm going to assume that you just have two probabilities. There's a probability if you go to a replica where you're preferred for a given term, and then all the non-preferred ones have some other smaller probability. So the non-preferred one should be less than the preferred one. And here's an example. Let's say you always miss cache if you go to a non-preferred replica, and you always hit cache if you go to a preferred one. I mean, this is insane. This is nuts, right? That's not going to happen, but it's still useful. So let's run with it for a second. It's useful as a starting point for this. So I'm going to talk about the balanced graph partitioning problem. You have a graph. You have some masses on each node, and you have some edge weights. So here the mass is 1, the mass there is 2. Suppose you want to divide this graph into, and the edge weights are sort of proportional to the thickness of the lines. So balanced graph partitioning says we've got K clusters, or here I guess R clusters. We want to divide it into. The total mass in each cluster should be roughly the same. So in this case, 4, 4, and 4. And we want to minimize the total weight of the edges crossing cluster boundaries. All right, this is a very well studied problem. And just to avoid, like we want it to be easy to find a feasible cluster, and so we don't want to have to run into NP hardness in that step, and which you would if you required exact balance just because of reduction to partition. So we're going to allow some node imbalance in the masses by 1 plus epsilon factor. All right.
What does an edge represent?
What is what?
What does an edge represent?
You'll see now. Okay, so what graph are we going to apply this to? We're going to take our training logs, and we're going to put all the terms on the left. We're going to put all the queries on the right. We're going to put edges from each query to each of the terms in that query. Okay. The node masses on the right will be 0. I'll tell you why in a sec. Node masses on the left will be the size of the postings list times the difference in the preferred versus non-preferred occupancy probabilities. The interpretation of this is that the total weight, the total mass, the total size of all the terms in cache would be, well, there's a baseline level for non-preferred. It would be non-preferred for probability times the size of your postings list. But then if you're actually in the cluster, then instead of non-preferred, you'd be using the preferred probability. So the point here is that the total, so if these probabilities were correct, then the total size of stuff in cache would be equal to some constant, which would just be the sum of the size t nt terms plus the node masses in your clustering. And so since all the caches are going to be equal size, we would like to have a balanced cluster on the left-hand side. Now, what are these edges? Again, you're going to have some probability of a cache hit, which would be, some probability of cache hit even on a non-preferred replica. But you have the increased probability of cache hit is pt minus nt if you go to your preferred one. And in that event, you save number of pages, cache misses. And so basically, the weight of an edge is how many cache misses you expect to save by on this particular term by sending this query to his preferred replica. And so, or conversely, it's the number of extra ones you get if you send on this term, if you send this query to this non-preferred replica for dress. So that's how we're building this table. And the reason we put a node mass of 0 here is because we want this node to go wherever TARS would tell it to go in the actual routing algorithm. And TARS would tell it to go to the replica that has the most savings per term, because that's exactly what these things are encoding. Fortunately, there's good software for solving these things. These are very, very difficult problems in theory and in practice, but there's METIS, there's the Karlsruhe KPAR. I've never known how to pronounce KAPAR, KPAR. And then we have our own homegrown thing, which is a big distributed version that can handle very, very large graphs. So, all right, so why do we care about that thing? Partitioning that graph is because of this equilibrium theorem. I hesitate to even call this a theorem because it's like a homework assignment. But I also the other thing that's funny about this is that this is a theorem whose hypothesis is never going to be satisfied. But I will just invoke George Box. This is a wrong model, but it is nevertheless useful. So it just says what I said before. Cache miss rate is going to be basically the cut size plus a constant. And then the cache size is going to be some constant plus the cluster term mass, which is why we're trying to do balanced partitioning. All right, don't want to dwell on that too much. But I'm really proud of this picture. What did we do here? So we solved this balanced partitioning problem. This is for the North American logs using 5 replicas. So we solved this balanced partitioning problem. And the question is the cut size in that partition actually predictive of anything? We hope it is. And here's the experiment we ran. We took a bias coin with heads probability F. We flip this coin. If it comes up heads, then, we flip that coin independently for each of the nodes in the graph, right? So we start with the partition that balanced partitioning gave us. We flip that coin independently. And if it comes up tails, we leave the node where it is. If it comes up heads, we move it to a random replica, which could be the one it started with. Right? We just start over and choose uniformly at random. And we did this for 1,001 different values of f from 0 to 1 in increments of 0.001. And each one of those experiments gives us a dot here, right? Each one of them gives us a partition. Each one of those has a cut cost, which we evaluated by just looking at the graph. And then each one of those, we get an empirical miss rate by just running it through the training logs, running the training logs using that, TARs based on that voting table. And this is what we get. And it's data, so it's not perfect, but there's a very, very clear correlation, and there's the least squared regression line in red. So yes, the cut cost really is a constant, the miss rate is a constant plus proportional to the cut cost. This is the one that's the point the balanced partition gave us. That's interesting. That one has an even better cut cost because it's an NP-hard problem and we didn't solve it exactly. And also maybe that might also violate balance. Anyway, but it does also have a worse miss rate. So, and this one was a random partition. So this is one of my favorite plots I've ever produced. Okay, iterative refinement, we are running out of time here. Yeah?
What about temporal locality? It sounds like you're just trying to converge to something that fits the entire trace, but a trace could have temporal phases.
Yeah, so what happens, it does, and so we run our trace through in order. So the question is temporal locality. So in the trace, we run our trace through in order, so whatever temporal locality is there is preserved. And when yes. So far, we've ignored that. But we're going to show you where we stop ignoring it right now. Iterative refinement, how do we do that? So we start with some voting table. We run the cache simulation on the training logs. We measure the actual cache hit rate. And that's where we're now paying attention to temporal locality. So whenever a new query comes, it has some term, fill-up, right? And if there's a recent fill-up, then we're going to have, that's going to contribute to a higher number here. Okay, now we're going to try just updating via a convex combination of the old and the new, train some new tables, rinse, wash, and repeat. All right, so what happens? Here's where we do this with the training logs. We take various step sizes, 1/4, 1/2, 1. 1 looks like the best because it converges really fast, and they all seem to converge to about the same value. But that is misleading because we shouldn't be evaluating on our training data. We should evaluate on our validation set. And then we see that, yeah, blue converges quickly to a crummy value. If you do it more judiciously, you converge to a lower value, albeit slower. So I don't really have a great explanation as to why these two things are the same. They're not converging to the same thing. They just have the same miss rate. A mystery that I will probably never figure out. Okay, simulation results. We compared several different things, so different numbers of replicas and different routing algorithms. So this is the one that was used before we ever got involved with load balancing. This is just taking a fingerprint of the query and routing it there. So basically random, but if you had a repeated query, it'll go to the same place. And we tuned the cache size so that the miss rate there would be 10%. This is where we do just a random clustering. So that was that upper right-hand point on that scatter plot that I showed you. This is the one we get from balanced partitioning. And this is sort of the best we could ever hope to do by just having a unified cache of R times the original size because we have R replicas. And it's maybe easier to look at this just in terms of its improvement over the baseline. So we see that random actually has a pretty big improvement just by itself. Balanced partitioning is quite a bit more. But obviously, if you were sort of had perfect resource pooling, you do even better. Now let's add in this iterative refinement that we showed before. Again, this is easier to do in terms of percentage terms. So if you look at random, it gets a little bit better with iterative refinement, but still not as good as the starting point for balanced partitioning. So that's interesting. And finally, some results from the production system. So what are we looking at here? This is CPU. So notice we weren't trying to optimize CPU. We're just trying to not ruin it. So if you do fingerprint load balancing, that's actually pretty crummy, right? This is kind of a heat map. So this is time. This is a normalized CPU utilization. So like each vertical slice is just a heat map for one particular point in time. And so we ran it with the fingerprint-based load balancing. Then this is just dynamically changing the weights, but but not doing any cache affinity, and then this is the full tar. So you can see that this is much better than that, and in going from here to here, we didn't ruin anything. These big bumps are an overload setting, so you run it at normal load, and then you bump it up by some percentage, so that's what that is. But here's the real payoff here. When you went from here to here, you got better CPU balance, but the flash I/O is basically the same. But now when we introduce TARs, the P99.9 is the same as the median was before. And that's the real win. Okay, conclusion, yeah, so iterative refinement helps, but the good starting point is even more important, right? Like balanced partitioning just by itself is already better than random with iterative refinement. Suppose that for whatever reason you can't run balanced partitioning, that's okay. Just use random. That already gives a big improvement. It's not as big as you could get if you had balanced partitioning, but it's pretty good. And one nice thing is that it's data independent. So if you have a data skew, well, it shouldn't hurt you. This is thanks to my co-authors, Kevin Aydin, Hossein Batani, Bahab Marokni, Aaron Schild, who was a student at Berkeley and an intern with us when he did this, now at Google. Ray Yang, Richard Zhuang. This is in VLDB. And some future directions. All right, better methods for training the voting table. This iteration loop that we did for the iterative improvement is not very principled. Maybe you can get faster or better convergence. You can think about trying to balance the query side as well, right? So right now we just ignore that and then just leave it for these multipliers to clean up afterward. If you had better balance, then maybe you could you'd have less to clean up. I would love to put this method on a more solid theoretical footing, right? Can we prove some lower bounds on the page miss rate, even if they're only instance by instance? There are many, many, many local optima for this voting table. I'd like to know how to avoid the bad ones. And here's an interesting one, stateful tars. So right now, each root just has this table that's loaded in at the beginning, but doesn't maintain any other state besides the multipliers. What if each root independently maintained its own view of the cache hit probabilities in real time based on what it's seen? That might be awesome. It would allow you to deal with distribution skew since you've trained your tables. But it also might just cause you to land in a worse local optimum. So interesting idea. We haven't tried it. All right, ran a little bit long. Sorry, guys.
Time for a few questions.
So maybe that's what, maybe this question referred to the local optima. So you're calculating, you're doing a simulation to calculate these probabilities,
Yeah.
which depend upon the current replica
Yes.
state.
Yes.
Is that right? And if is that right?
The simulation, so you start with what we do is we start with an empty cache.
Okay.
We run the logs through once to warm up the cache, which, as I said, it goes through like more than 95 full cache fillings and cleanings, right? So it's fully warmed up.
Okay.
Then we run the logs through again into this warmed up cache.
Okay. And then you calculate the.
And then, yeah, so every time a query appears, you look at the terms in that query, look to see if those terms are in cache, and you record a 0 or a 1 in the numerator and a 1 in the denominator, and then at the end you just take total numerator over total denominator. That's your cache hit rate for that term. So you're doing what TARS would do, and then you're just calculating this on the side and observing, and then using that to create a new voting table.
And so the local optima here refers to the fact that if TARS was not doing things correctly, it might just enter a situation where you eventually you're directing in the right way based on what TARS is doing, but you could have done something completely different and you could have done much better.
That's right. Yes, David.
Coming back to Phil's question.
Yeah.
Temporal locality.
Yeah.
Different moments in time are very different, and it seems you have a very smoothed approach to how you adjust to evolution and not shocks to the system in terms of impact of what queries look like. Is there any thought that this doesn't matter, or is that it's just too hard a problem to sort of think about sort of the rate of change as being a function of being able to detect shocks? Or
So this, I didn't tell you the whole architecture. This system is sort of the bottommost piece of web search. Above it, there are some other caches that attempt to absorb most of these shocks, right? So if you have some term you've never seen before, so it's not even in the table, but is all of a sudden trending on Twitter or whatever, I refuse to call it anything else, then that cache will pick that up, and that'll be cached like before it even gets to the system.
So a question I'm sure you aren't going to be able to, allowed to answer. So what fraction of queries go to reach this sort of baseline structure rather than?
Reach to where we're going here?
Yeah.
Again, I can't tell you exactly, but let's say like broadly more than half and less than 90%. Yes?
Question about your graph partitioning algorithm. I mean, the ones that people use are, recursive and coarse in the graph and use fiducian mates to improve it at each level. I'm just wondering, do you have a different idea?
Right. So that is indeed what Metis and Ka-Par do. We do something much simpler. So we basically create a linear embedding. So we use something that we call affinity clustering, but it's really Borufka's algorithm for min-spanning tree, right? So one layer of Borufka's algorithm, basically, so each node grabs its closest node, which in this case means highest weight edge, right? And so now there's this arborescence, and you collapse each arborescence into a node, and now we're going to embed each cluster contiguously on the line, within that cluster, and now we recurse on those clusters to get some embedding on the line. And then, actually, sorry, we collapse. We can do it the other way around too. So we can take those clusters and we can do another round of Borufka to cluster, another round of Borufka to cluster. And so basically you end up with this, I should have included the slide. I actually had a slide showing this. So you end up with this hierarchical clustering, and then you just do a linear embedding based on that. And now you can just chop using parallel knives. But then we also do some fiddling at the boundaries to do some local optimizations. So this does not, so on small graphs, this does not work nearly as well as those others, but it's much more scalable because this is very parallelizable and distributable. Yes?
So I noticed like the paper is 2019. So is this still what Google does in production?
This has been running in production since 2015 and is still running in production. It's very successful. Yeah. So you can multiply the number of queries per day by 10 years. It's a lot of queries.
Do they give you like a certain percentage of the savings for your salary?
If they did, I'd be in Maui right now.
All right, let's thank Aaron again.